So here are some other examples that can be considered for calculation, right? Now we look at segments and offset scheme, and this is an important point, right? Segments and offset scheme allows relocation. That is a very important point. Segments and offset allow relocation, right? So we discussed that basically if we are talking about the code segment, right, we have this CS register and the IP register, right? The main idea of this concept is basically whenever we assemble an assembly language program, right, all the addresses that are generated, the addresses are generated in terms of the offset addresses. They are not generated in terms of the physical addresses. What do we mean by that? Just to have an example, let's now look at this example that we have over here. This is how basically the assembly language program is stored in the memory, right? So for example, this is the 0000 address, 0001, 0002, 0003 and 0004 address. So first of all, at the first address the opcode byte is stored. For example, it can be the move byte, add, right, whatever you can have, move, add, etc. So first is the opcode byte. The second location or second memory address holds the data bytes, and the third also, if it is an 8-bit data, it would be only held in one memory location, and if it is 16-bit data, it would be held in two memory locations. So first, so opcode 1, this is the data of instruction 1, data of instruction 2. So over here instruction 1 is complete. Then of course from address 0003 we start the second instruction, opcode 2, followed by its data, and we are assuming that the data of instruction number 2 is 8 bits in length. Okay, so these are the two instructions and how they are stored in memory. So coming to the again to the same point, we always define in terms of offset addresses, we don't define in terms of the segment addresses. What do we mean by that, right? We see that our program is stored at the offset address 00002 0004. So this is the address on which our two instructions and our entire program is stored. So let's say if in the first case my segment address is 0000, and we know that the offset address is 0000, right? So what would be the physical address? Quickly, CS into 10H, which is 5 zeros plus 0000H. So we would have the physical address, sorry about that, 00000 hex, right? Now let's say if we have the same offset addresses, let's say the program begins with the same offset address now, so this offset address would remain the same, but now our segment address has changed to 1000H. So what would be the physical address be? Quick, 1000 into 10H, 10,000 plus 000H, it would be the 10,000. Sorry, these are all hex values, okay? So the physical address for the first case is 0000H, and the physical address for the second case has changed because the segment address has changed. So moral of the story, if the segment address changes, the physical address changes, even if the offset address remains the same. So this is the main idea and the main point. If we assembled a program and defined the addresses in terms of physical addresses, every time the segment address changes, since the physical address would change, we would have to assemble the instruction again. For example, if in the first case we executed instruction as JNZ 0005. So what actually we meant was we were moving to the offset 0005. But now when the segment address changes, this 00005 would translate into 10,005. So this instruction would need to be changed if we are talking in terms of physical addresses. So Intel arrived on a clever idea that this did not define addresses in terms of physical addresses, they defined addresses in terms of the offset address. So whatever may be the physical address, the offset address would remain the same. For example, 0005 offset address would always mean that we would be jumping to the offset address 0005. It might be in segment 0000H, it might be in segment 1000H. So the beauty of this is, since we are defining addresses in terms of offset addresses, we are defining addresses in terms of offset addresses and not in terms of physical addresses. So the program might be running in any segment, but the offset address would remain the same, they won't change. So the assembly language program can be relocated to any segment easily. So that is basically the concept of relocation. So again, like we have discussed before, this is the same thing that we have discussed. The different segments and their offset address. CS has an offset IP, DS has an offset SI, ES has an offset DI, and so on and so forth. But the idea of relocation would be the same in other segments also. So all addresses that are defined would be defined in terms of the offset addresses. So the segment changes may be changed for any segment, but the offset address would remain the same. You can read more about it from page 59 to 63 of Barry B. Bray book. You should read this, okay? Now some points about the 8086 internal architecture. This is the internal architecture model of the 8086 microprocessor. As we can see that this microprocessor consisted of two parallel separate units. One was the BIU or the bus interface unit, and the other was the EU or the execution unit. Intel introduced the idea of parallelism in this processor because the BIU and the EU could execute parallel to one another, right? They could carry out operations parallel to one another. As the name suggests, the bus interface unit dealt with the interface with the system bus. So all the external bus signaling, right, or internal bus signaling for that matter, address bus, data bus, and control bus. Remember that there are the three buses that we discussed before: address bus, data bus, and control bus. They are common both to the inside of the microprocessor and both to the outside of the microprocessor. So this bus control is the responsibility was the bus interface unit. So we can see that we have all these segments addresses: extra segment, code segment, stack segment, data segment, and instruction pointer. These are the registers that represented the bus interface unit. And as we have discussed before, they were used in calculation of the physical address that would be specified to the external data bus. Then of course we had the execution unit or the EU. As the name says, it dealt with the execution of the instructions. So as we see that it dealt with the execution of the instructions, the arithmetic and logic unit or the ALU was an integral part of the execution unit. We also had the arithmetic and logic unit that would carry out all the operations. The operands registers would be there, and especially the flag register was there to indicate the result of the execution of an arithmetic and logic instruction. Of course, we also had this AX, BX, CX, and DX registers that were broken down into the 8-bit AH, AL, BH, BL, CH, CL, and DH, DL. We also had the offset registers or the pointer registers over here: stack pointer, base pointer, source index, destination index. Now this control system was the generic control system that would deal with the control of the bus interface unit and the execution unit. As you can see, these were the buses that were shown, address bus is shown and control bus is shown. The data bus is not shown, but it was also there because system bus includes the control bus, address bus and the data bus. So one of the most important concepts of the bus interface unit was the instruction stream byte queue or instruction queue. Intel's 8086 was a processor so much ahead of its time that Intel had introduced the concept of cache in this particular processor, right? And since it was a rudimentary cache, a very simplified cache, they called it just an instruction byte queue. And the concept of the byte queue was both of a cache and both of a instruction prefetch operation. Let's see what is meant. For example, when the execution unit was executing instructions such as move AX, let me write it again, move AX comma BX, right? It is an internal instruction in the sense that in order to execute this instruction, memory access is not required, because the source operand is in BX and the destination operand is in AX. So the beauty of this instruction queue was that when the execution unit was executing this instruction, this kind of an internal instruction, since the external system bus was not being used, the bus interface unit could make use of this time to apply addresses to the external system bus and get the next instructions loaded into this queue. So it was a 6-byte instruction queue in which the instructions could be loaded. So when the processor would need the next instruction, it won't go to the memory, it would first go to the instruction byte queue or the cache, and if the instruction was there, it could fetch that instruction from this memory much faster as compared to external RAM. So this was the concept of instruction cache as well as instruction prefetch into that particular cache. A really advanced concept at that time. After that, we can look at just some internal architecture continued. There can be the registers of the Intel 8086 processor. There were general purpose registers, special purpose registers, and we have already discussed that it is divided into two units: the bus interface unit and the execution unit. And we have discussed this idea about these two units in detail. So that's all for this discussion. Thank you for watching.